let's have our second speaker of the afternoon session, Guido Bellomo, Entangled Discord, when quantum correlations precede quantum systems.
Okay, good afternoon to everybody. So, my talk is going to be also about some notion of quantum correlations that we understand that it is relative to the way that one chooses to partition the system into subsystems. But also, I would like to present some generalized framework to understand this subject. So, it has many common points with the talk of Nathan. If you dislike his talk, you are going to hate mine because it is less precise from a mathematical point of view and perhaps less clarifying, but I'll try to do my best. So the guiding question for the talk is going to be how to better understand quantum correlations in standard quantum mechanics. So the idea is the following. Correlations are usually prescribed when we have some subsystem structure in the system. And it turns out that we are going to see that this idea makes the notion of quantum correlations relative to the way that one partitions the system into subsystems. But it can be generalized further if we establish some notions that do not depend on subsystems, rigid subsystems decompositions, but rather on observable prescriptions. This kind of generalization is not in vain, and it has many information theoretic implications. I come from the community of physics also, so I work during my PhD on quantum information. Many of these information theoretic implications of this kind of understanding of quantum correlations is what I have been doing during my PhD. So the final goal is trying to present some different, maybe unified and maybe reasonable top-down framework to understand these things. In first place, I think that it's funny to remember this passage, these words by Asher Perez, a very known physicist, that says that a quantum system is a useful abstraction which frequently appears in the literature but does not really exist in nature. In general, a quantum system is defined by an equivalence class of preparations, and this resembles the idea of bundle of instances that Olympia mentioned in one of her talks. And he continues saying that there is some ambiguity in the way one defines a quantum system, at least from a physicist's point of view. And we must be content with the back definition, he says. A quantum system is whatever admits a closed dynamical description within quantum theory. Here he gives a couple of examples. And finally, he concludes that while quantum systems are somewhat elusive, quantum states can be given a clear operational definition based on the notion of test. We can define a state in the following manner. A state is characterized by the probabilities of the various outcomes of every conceivable test. So this is just some kind of off the record, but the thing is that if a quantum system hasn't a real strict definition from this point of view, it is even more problematic to define subsystems, maybe. So, from a mathematical point of view, we know that when we are in standard quantum mechanics, we start with a Hilbert space associated to a certain quantum system, and there we can work defining the states, the possible states of this system, and finally, the evolution of these states is going to be dictated by some Schrödinger-like equation. And a subsystem has to do with some kind of factorizability, of the Hilbert space in such a way that we can individuate these subsystems. And then if this kind of structure exists, we can compute the reduced states via some partial trace operation, and we are going to have some dynamical master equation in general. So what about quantum entanglement? That is maybe the most known kind of quantum correlation. Okay, we can remember this words by Schrödinger, who says that another way of expressing this peculiar situation is that the best possible knowledge of a whole does not necessarily include the best possible knowledge of all its parts, even though they may be entirely separate, and therefore virtually capable of being best possibly known, that is, of possessing each of them a representative of its own. So this way of understanding quantum entanglement, I think that it's very clarifying when trying to generalize the notion of entanglement to different scenarios. So the idea is that if we consider the whole convex set of quantum states, in the border we have the extremal states that are the pure states, and they are related to complete knowledge in the sense that there exists a quantum state, a quantum test, that yields certainty. But on the contrary, mixed states are related to incomplete knowledge in the sense that every quantum state test yields some degree of uncertainty. So this idea of complete or incomplete knowledge is related to the mixedness of the quantum states. In the bipartite scenario, it's another way to put this is that not every pure state is also pure in terms of its parties. So, for example, if we have an A-B system, A-B being the two parties, then we can have this first case where the state is factorizable, it's a tensor product of both parties, but we can have in general a state that cannot be written in this way. And so in the second case, complete knowledge of the global system does not imply complete knowledge of its parties. And behind this behavior is the idea of non-separability. Then for mixed states, separability is usually defined extending this state factorizability idea. So we have this kind of formula to define the separable states. And in the whole convex set of quantum states, we have a subconvex of separable states. So the common intuition to talk about quantum correlations starts by prescribing some subsystems that, putting all together, form a given system, and this system generally is associated with Hilbert space, that is the tensorial product of the constituents parts. And the correlations are going to be defined between these subsystems there. But as Harshman said, this is not always the case. For example, there's no factorization in this way when we have undistinguishable particles. So due to symmetrization of this problem, we have no tensor product structure in this trivial way. So we have no subsystem identification, and the partial trace is not well defined. So the usual way to talk about entanglement is not valid. So here you have a first problem, in some sense. A second limitation comes when we observe that even when we have one factorization, we indeed have many compatible ways to factorize, to partition our system. So before giving one physical assumption for example, locality, a locality prescription, we don't have a way to privilege, to prefer one decomposition over the other. And a known example, a very known example, is the one of the hydrogen atom in the ground state that can be described in terms of proton plus electron or center of mass plus relative position particle. And generally the system is solved in this second scenario where the center of mass behaves like a free particle and the relative position is affected by a central potential. So due to the ratio of the masses, we have the relative particle eigenstates are almost the electronic states. And while the ground state is separable in this second decomposition, it is entangled in the first decomposition, in the sense that Hartmann explained before. So we have multiple compatible decompositions of our Hilbert space, and so the notion of quantum entanglement becomes relative to each of them. So, given these alternative factorizations, okay, I'm not going to repeat this example, that is really the same, exactly, but we can have, for example, a first local description of our system that induces this tensor product structure here. And I take care not to talk about local or a different local decomposition here. I named this as a relevant algebra of observables, where relevant means nothing or everything. It's just what I want to decide to be relevant for some sense. For example, my criteria could be just that we have local accessibility or experimental accessibility or some kind of metaphysical assumption of symmetries or invariances involved in this case. But the thing is that mathematically it's possible to define different algebras of observables that induce different tensor product structures, and for example, every Bell state in this first scenario is non-entangled with respect to the second case, as was proved by Zanardi. And also we have these two other works by De La Torre and collaborators and Hirschman and Rene that were mentioned before. And it's important to take note that this is not the case for optional mixed states, where things are more involved. So we have 3 points here that must be analyzed with much care. First, there are cases when we have no subsystems identification, but there are also cases when the decompositions are multiple, and maybe there is some kind of ambiguity in the definition of the typical quantum correlations like entanglement or discord. So I would like also to remember this work by Paolo Zanardi, where he says that the fact of considering all these possible decompositions on the same footing that amounts to establishing a democracy, he says, between the different tensor product structures, provide a relativization of the notion of entanglement. And without further physical assumption, no partition has an ontologically superior status with respect to any other. So an important question is how or why to privilege a given TPS. So there are many arguments that one can pose to say that there is some privileged TPS over the others. For example, experimental accessibility or Galilean and dynamical invariances, as Nathan explained before. And I like this passage here in one of the last words by Nathan, where he says that the collection is created around a theme. Symmetry selects preferred quantum structures, and preferred quantum structures instantiate observation, information, control, and interpretation naturally. And the ironic quotes, he says, around naturally indicate that this may be an idiosyncratic and possibly recursive definition. So we are not really sure if it is enough taking into account this kind of invariances to select preferred decompositions. But the point is that we have multiple decompositions in many cases, and it deserves to be analyzed what is the relative notion of entanglement or any other type of quantum correlations with respect to these different decompositions. So, to define some relativization of this notion, and in a way that is subsystem independent, we can recall this work by Barnum, and the important points are the following. It is possible to define a weaker notion of entanglement without relying on correlations between subsystems, and instead it is necessary to select a relevant observable algebra, as I said before, and there may be multiple possible subsystem decompositions, but given a set of relevant observables, it is not always possible to define a tensor product structure. So we can have multiple, or we can have no decomposition at all in subsystems, but if we have a notion of entanglement that is relevant to the observable algebra, that is not a problem. So the idea is that one starts with a whole closed system, and one defines the states there, and then one selects by means of some criteria a relevant algebra of observables that is included, a subset of the whole observable algebra, and then one can compute in a manner that Barnum explains in this paper the purity relative to the relevant observables. So this way one can define a generalized notion of entanglement that resembles the observation by Schrödinger.
What is relevant observable?
What is?
What is relevant observable?
Whatever you want. It is, but the thing is this. You can define mathematically any subset of observables, and you can do all this mathematical construction independent of the physical assumption behind that. Then, obviously, we are doing physics, so it is desirable to have some physical interpretation for that mathematical construction. And for example, you can have
physical interaction to measure this observable?
Sorry.
Do we need possibility to measure this observable to be relevant, or no?
I am not really sure. If you have experimental accessibility, then this experimental accessibility could be a reason by its own, right? But it may be that, for example, we have some symmetries or invariances, dynamical invariances, that are related to some other observables that nowadays are not experimental accessible. And I think that it deserves also to study that case, because experimental accessibility is something that changes in time, right? Yeah, I'm not sure if I answered the question. No, it's okay. So there are cases, but only some of them, when this relevant subalgebra is going to induce some subsystem structure, some tensor product structure over the whole Hilbert space. And in that case, we are going to recover what we usually speak about, that is correlation between subsystems and the usual notion of entanglement. And in general, this kind of structure is going to be related to some properties of the way in these observable, relevant observables are decomposed. So, as I said at the start of my talk, all this relativization has information theoretic implications, and many of them are related to computational or communicational problems in quantum physics. I like this phrase by Jeffrey Babb, who said that recent work on quantum information has led to a shift of focus in which the puzzling features of quantum mechanics are seen as a resource to be developed rather than a problem to be solved. And I think that this passage is also related to the question because these dynamical changes in the physical theories and the physical formalism makes that something that were not experimental accessible before, or that were previously not taken into account because we haven't seen a problem there. Now it is very different from nowadays perspective. So I'm going to mention just two works here. One of them, as we said before, by Barnum, who defined this generalized entanglement and related to the phenomenon of quantum phase transitions. They showed, for example, that this generalized notion of entanglements related to the points where the quantum phase transitions are produced, for example, in the Lipkin model that are resolved with these beta ansatz. And during my PhD, I have been working on some quantum implications of the non-discordant states or classically correlated states, and some implications of this kind of relativization of discord in terms of monogamy relations, of quantum correlations. I'm not going into details of all this. It's just to mention some of the information theoretic implications. And just to say something about discord, the thing is that when we have mixed states, there is another way to define what is quantum. It's a controversial, in some sense, definition, but it has a lot of studies nowadays. And it says that a non-discordant or classically correlated state is one that can be locally accessible by measurement, or in other words, it can be measured locally without disturbance of the joint system. And the scheme is the following. For pure states, we have just a separation between entangled and non-entangled or separable. But for mixed states, we have this categorization, but also we have another way to understand this separation between classically correlated states and quantum correlated ones, where the classically correlated are just a subset of the separable states. So this notion of discord can be relativized in turn, as it was done with quantum entanglement, and we think that it deserves to be studied separately. These classically correlated states of this notion of discord is related to decoherence, to locally extractable work, and other local things like measurement disturbance or accessible information. So the top-down view that we would like to develop has to do also with a closed system approach. We start with the set of observables of the whole system that is associated to the algebra of observables acting on a certain Hilbert space.
You have finite time left.
And the relevant set of observables, wherever it means, is a subset of the whole set of observables. And we have, in turn, a relevant subalgebra here of observables. And in this scheme, we can define these relative notions with respect to relevant observables. And for example, Barnum defined entanglement as relative purity, and we have many arguments to think that discord has to be with relative coherence, has to do with relative coherence with respect to the relevant observables also. So this closed system approach, this top-down view, not only implies some relativity of the correlations with respect to the relevant observables, but also a relativity of the coherence, for example, like it was explained before. In summary, what we have seen is that quantum correlations are relative to relevant observables, that separability has to do with relative purity, while classicality has to do with relative coherence. The problem of the subsystems prescription could be solved if we adopt a top-down view plus some observable relative notions. And the relativization of entanglement discord has information theoretic implications that deserve also further analysis. So these two things in red are the ones that are work in progress, and we have to study in more deep. So thanks for your attention.
10 minutes after the coffee break.
I agree that the Zanardi work and all of the associated work on the relativity entanglement is really important, and but there's something that I feel is overlooked in that, and maybe I'm confused or something, but the hydrogen atom example that's used a lot, it seems as though that's sort of stating, look, there's this completely democratic equivalence between the different kinds of observables we could use, but I don't see them as equivalent, because I see them as there's a democracy that's broken there because they are a bound state as the hydrogen atom. So in that particular case, I mean, there may be other cases like that where if you look at, that there are subsystems that as free systems are subject to a description with a scattering matrix that gives you a pole and, many possible poles, one of them being the hydrogen atom. And I see that as almost kind of a phase transition maybe, that there's a physical interaction going on there that breaks the sort of otherwise democracy of the different observables pertaining to that system. So in that particular case, I mean, I'm sure there are lots of cases where it's just completely relative, but in that case it seems to me there's a sort of a bottom-up reason for an inequivalence of the kind of description that you can give in the two cases.
I totally agree that I just presented that example because it, for historical, and it's a classical example that is always presented, but I agree that this democracy must be taken with much care, because it's just a mathematical democracy, but then one has to endow the model with the necessary physical assumptions to give some sense, some physical sense to each one of the possible decompositions. And maybe, for example, in this case, the second decomposition has no physical, is not as important from a physical point of view as the former.
Right. I mean, I think in that case, I think in some cases it might be harder than others to argue that one is a more relevant or more physically natural decomposition. But in this case, I think there's a very strong argument that it's the natural one, because if you try to view them as equivalent, you're disregarding a part of the Hamiltonian, and you don't want to do that. So if you want to take into account all of the actual physical interactions that are going on for the system and complete your Hamiltonian that way, then I think that's going to break the equivalence in that case.
Yes, okay.
I believe there is a simple picture. Everything can be described by pure state. There is no need for mixed state. Take a bigger system, everything mixed state. And then there are some entities which interact, like electron and proton. Now you can consider some kind of average interaction on time or kind of question when you can interact with an atom. But it's just approximation. It's sometimes useful, but a real interaction with electron and real interaction with proton. So we can say if electron and proton are entangled or not. Talking about atom, it's for kind of a shortcut which might help us to some calculation. It's not fundamental thing. We have only fundamental entities like electron and proton or any kind of systems. System which we can directly have physical interaction. So I don't think all this considering democracies, there is no democracy. Physical interaction happens only to particular things, not to other things. You make some kind of playing with algebra as a representation, you do not have direct physical interaction. Direct physical interaction only for some particular thing, and so the question, if there is entanglement, if there is no entanglement, have definite answer and not relative to anything.
Okay, but even when considering only experimental accessible degrees of freedom, for example, there are many possibilities.
There is no direct interaction to atom. In practice, you have, but really the interaction into electron and proton, and then you can say that effectively you'll get interaction to atom. And then you can say effectively for a particular experiment, it's useful. I don't think no one needs it, because sometimes it's really useful. You can effectively have interaction to an atom. But really, the explanation is that you have interaction to an electron and to proton, and then you explain why in reality it's come out, in the end it's look like an atom. It's much would be simpler to calculate it when you look interaction to an atom, but it's not really. Really you interact with electron and proton, and only electron and proton have basic interaction. So you can always answer if there is entanglement in particular situations, there is no. And this is only when you look at these entities which have direct physical interactions.
Okay, but I'm not trying here to get the real physical picture. Just, for example...
I don't think just way to...
Let him answer. I would like to hear him.
No, okay. I agree with what you are saying, but I'm not trying to get the picture of the reality in some sense. What I'm trying to do is, for example, to weaken the notions of quantum correlations because it has many applications. For example, from an experimental point of view, an information theoretic point of view, you can perform some quantum tasks just when you have entanglement between some degrees of freedom.
But this is physics philosophy, not...
No, this is physics. This is physics. They are using...
How the world, how the nature is, how the world is built.
We are not in a place where we want to calculate build a machine.
This is not
engineering.
But if you have done...
I'm sorry, but he's saying that this is something that is used in physics to as a resource for quantum information. He's not...
Has nothing to do with nature.
Also, if you have two compatible physical pictures, then you need some extra assumption to privilege one of them. And
you call it assumption, I call it existing physical interactions.
One more question, maybe, then we'll have a break.
Just to understand each other, because I just have the same idea that Lev has. One thing is setting the theory. Now, the theory, that's in Nathan talk, there was a starting Hamiltonian, for me means Schrödinger equation. So that everything is fixed. All the rest I take as analysis. If the theory is fixed, I don't introduce any new physical facts. It's just analysis. Now, doing analysis is clearly, I mean, we know from classical physics, more convenient to have some variables than the others, to use some separation instead of some others. But the physics is fixed by the beginning, by fixing the Hamiltonian.
Okay, but here, for example, there are more than just multiple possible decompositions. For example, Barnum, when he defines this notion of entanglement with respect to some relevant observables, we can only stack with the original relevant observables, the local one, for example, but even in this case, the notion is weaker, is more general than the one that one usually has in the literature.
Yeah, but for application we agree. But on the
No, but I'm not
from
talking
the
about
fundamental
applications.
level,
Uh,
there is electrons, protons, and there is an Hamiltonian describing
If
how
you
they
define
interact.
entanglement,
I think we have
sorry,
to-
a last observation. If you define entanglement just as the non-separability in terms of the Werner description of a separable state, or if you define entanglement as the property that the purity decreases when you consider a subsystem, then the two definitions are not the same. So the Barnum definition of entanglement is not the same. It's also only the same when you have a tensor product structure of the whole Hilbert space. But if not, it's different.
So this
there are
conversation
physics there.
should continue. I haven't even added my comments yet, and they're gonna blow you. Well, anyway, but let's go to coffee break now and continue
Thank
this
you.
discussion. Thank the speaker again.